So, you know how asking an AI to read a really long document feels like it takes an eternity? Well, large language models are unbelievably powerful, but that power comes at a huge cost, especially when you're feeding them massive amounts of text. Today, we're diving into a new paper that introduces this fascinating and, frankly, incredibly clever solution called GemFilter. It's a method that finds the crucial gems of information really early on to just dramatically speed everything up. Okay, so here's our game plan. We'll start by digging into the core problem, what we call the long context bottleneck. Then we get to the really cool part, the aha moment of finding these gems in the early layers. From there, we'll break down exactly how GemFilter works, look at the math that proves its efficiency, put it under pressure to see how it performs, and finally, zoom out to see why this whole thing is such a big deal. All right, first things first. Before we can really appreciate the elegance of the solution, we've got to get a solid grasp on the problem it's designed to solve, and that is the long context bottleneck. I mean, modern LLMs like Llama 3.1 or Gemini, they can process these enormous inputs. We're talking up to 120,000 tokens, sometimes even more. But trying to feed them an entire novel or a dense financial report, well, that comes at a massive cost, both in raw processing time and in the amount of super expensive GPU memory you need to have. Yeah, this ability to handle huge volumes of text is a total game changer, but it creates this really significant bottleneck. And the slowdown primarily happens during a specific phase that comes before any text is even generated. It's called the prompt computation phase. So, this is the crucial point to understand. Before an LLM writes even its first word of a response, it has to do this massive heavy lifting calculation on the entire input. It reads everything to build what's called a KV cache. You can think of this as the model's short-term memory. It stores all the important contextual information, the keys and values, that its attention mechanism will need later on. For short prompts, no big deal. But for long documents, this initial step is an absolute resource hog. It's where all the time and memory just get devoured. Okay, so let's move on to the paper's key discovery. This is a really fascinating insight into how these models actually process information. Turns out, they're a bit smarter and maybe a bit more intuitive than we often give them credit for. This right here, this is the core insight of the entire paper. The model doesn't need to process the whole document through all 30, 40, or 50 of its complex layers to figure out what's important. Instead, it spots the gems, the most relevant bits of information, incredibly early on in its neural network. And this is just a brilliant illustration of how it works. Imagine you give the model a long text with a question tacked on at the end. Well, just by looking at the attention scores that come from that very last token, the question part, in a super early layer, the model has basically already highlighted which parts of the text contain the answer. It's an amazing discovery. It's almost like the model sends up this subconscious flare pointing right to the answer before it even consciously formulates it. So, this fantastic insight leads directly to a really elegant solution, the GemFilter algorithm. Let's break down how it cleverly leverages this early layer intelligence to build a much more efficient process. Okay, before we dive into the algorithm itself, a super quick refresher on self-attention, which is the heart of how transformers work. For any piece of text, the model generates three matrices: a query, a key, and a value. By comparing the query of one token to the keys of all the other tokens, the model figures out how much attention, or importance, to assign to every other part of the text. It's this mechanism that GemFilter so cleverly exploits. So here it is, this beautifully simple four-step process. First, it does a quick, lightweight pass, running only the first few layers of the model over the entire document. Next, it does the critical selection step. It uses those attention scores from the query to pick out the top K most relevant tokens, the gems. Then it compresses everything, creating a new, tiny input sequence made up of just those gems. And finally, it does a second pass, feeding that super compact, gem-filled sequence into the entire model to generate the final answer. And the result of this? It's an absolutely mind-boggling level of compression. The paper gives a real-world example where an input of over 108,000 tokens got squeezed down to just 100. Let that sink in for a second. It found everything it needed in less than 0.1% of the original text. That's a compression factor of over 1,000 times. Just incredible. Now, this two-pass approach isn't just a clever trick. It is mathematically, provably more efficient. So let's take a look at the complexity analysis to see exactly why that is. Okay, let's break down the math here, because it really tells the story. The key thing to focus on is the difference between M and R.
In a standard model, the time complexity for prompt computation is proportional to m, which is the total number of layers in the entire model. But look at GemFilter. Its time complexity is proportional to r, which is just the small number of filter layers it uses in that first pass. Since r is way, way smaller than m, say 13 instead of 32 for a model like Llama 2 7b, the time required for that initial costly step is just slashed. The same logic holds for GPU memory. You're loading far fewer model weights, so you use far less memory. It's a fundamental improvement in efficiency.
So, the theory is solid, the math checks out, but the real question is, how does it actually perform in the real world? Let's put GemFilter to the test and see how it holds up on some really tough benchmarks. And the results are seriously impressive. When compared to SnapKey, which is already a state-of-the-art optimization method, GemFilter delivered a 2.4 times speedup in that critical prompt computation phase. That is a huge improvement. On top of that, it cut peak GPU memory usage by 30%. That can literally be the difference between being able to run a model on your hardware and not. But what about accuracy? I mean, you'd think that by throwing away 99.9% of the text, you'd lose some precision, right? Well, here's the kicker. In the classic needle in a haystack test, where the model has to find one specific fact buried in a sea of irrelevant text, GemFilter doesn't just keep up, it actually performs better. It seems that by filtering out all the noise, the model can focus more clearly and find that hidden needle more reliably than when it's forced to look at the entire haystack. And this isn't just a one-off result on a single task. Across the huge range of challenges in the long bench benchmark, everything from question answering to summarization, GemFilter consistently maintains high performance. This really proves its effectiveness and reliability as a general-purpose tool. Okay, so let's wrap this all up by zooming out and summarizing why GemFilter is so much more than just a clever optimization trick. There are really 4 key takeaways here. 1, it's simple to implement. 2, and this is huge, it's training-free. You can apply this to existing, pre-trained models today without any costly retraining. 3, it's broadly applicable across many of the most popular model architectures out there. And 4, and for me this might be the most exciting part, is the new level of interpretability it offers. For the first time, we have a simple way to ask the model, hey, what parts of this giant document did you actually think were important? We can literally look at the gems it picked out and get a real glimpse into its reasoning process, which has always been a massive challenge with these black box systems. This research doesn't just give us a practical tool to make long context AI faster and more accessible. It also really deepens our understanding of how these incredibly complex systems actually think. And it leaves us with a pretty compelling question to ponder. If we can see how an AI learns to find the essential information, what does that tell us about its ability to learn what to ignore? The answer to that could very well shape the future of building truly efficient and intelligent systems.